Okay, so now that we have this expression dl total by dt equals tau external, let us apply this to a problem. Okay, this is one of the examples in the textbook. It's a useful example. Let us apply this and let us figure out how to find the net angular momentum for a system of particles. Okay, so here's what you've been given. You've been given a system. We have a pulley. Okay, and then you have a mass here, say M2. Then you have another mass here, M1. And let us say that the pulley essentially is, all the mass of the pulley is in the ring. Okay, so it's a ring and it has a mass of some m. Okay, now what's happening is that at any time, okay, when you let the system go, let v be the velocity of the blocks, and let us assume that the pulley, there's no slippage here, so the speed v with which each particle of the pulley moves is also v. Okay, and we can use all this to find the angular momentum of the system. Okay, and we'll find the angular momentum about the axis, about this axis, okay, for the pulley. And if you look at the angular momentum, if you remember this is equal to the momentum times the moment arm. So for the block M1, the momentum is M1 times v, and the moment arm, oh by the way, I didn't give you the radius. The radius of this is, let's say, r. Okay, and the moment arm is simply the value of the radius, okay, for block M1 about this axis, because that's the perpendicular distance of the of this momentum M1v, say this is M1v, and the perpendicular distance that it makes with the axis is r. Okay, similarly for the second block, it is going to be equal to M2 times v, okay, once again times r, because the moment arm that the momentum M2v makes, okay, is r. And then for the ring, since each particle on the ring is a fixed distance r, and since each particle on the ring also moves at speed v, the total momentum, angular momentum for the ring will simply be equal to its mass, which is capital M times v times r. Okay, so the total angular momentum is given by this relation. Now what we ask is, we can use our expression that dl by dt is equal to tau external, and we can use this to figure out the acceleration of the masses. I know you can do this by other means, but we can use this to figure out the acceleration of the mass, and let's see how we'll do this. Okay, the concept is going to be very simple. What we have is, we already have this L, so dl by dt is simply equal to m1r times dv by dt plus m2r times dv by dt plus mr times dv by dt. Now dv by dt, as you all know, is simply a. So you get m1r plus m2r plus capital M times r multiplied by a. Right, we have this. Now what we can do is we can figure out the net external torque. Now let's look at all the forces that are acting here. Okay, and if you look at this system, okay, we have the force M1g pulling the system down, which is basically what is the driving force in the problem. Okay, so let me draw this thing again here so that you see this. Okay, so we have M1g driving everything. Okay, then we have M2g pulling it down, and then the contact force, which is equal to M2g pushing it up. Okay, and then we have the force of tension, okay, that is acting about this axis. We're going to find all torques about this axis, and then we also have the axis itself exerting a force that is going to be responsible for some torque. Okay, but we know that since the distance of the force that the axis exerts, so whatever force this axis exerts, so whatever force it may exert, okay, this force is going to be responsible for zero torque about the axis itself, because the moment arm is zero. So that torque will be zero. So tau to the axis is zero. The torque due to M2g and Fn, they're going to be in equal and opposite directions about this point. They do produce a torque, but they're in equal and opposite direction, and so that torque ends up being zero. So the only force that actually gives you a non-zero torque is M1g, and that is equal to M1g times the moment arm, which is equal to r. Okay, so m1g times r is the torque. So we have this net external torque. So now we can use our expression that tau external is equal to dl by dt. So what we end up getting is m1gr is equal to m1r plus m2r plus mr multiplied by a, and this ends up giving us a as m1g over m1 plus m2 plus m. I can cancel out the r's on both sides. Okay, now you could have obtained this relation without going through all this. You could have just drawn, used Newton's laws, drawn the free body diagram for all the bodies, accounted for the torques for the ring, and then attained the same answer. Check it out and make sure that you get this. Okay, all right, that's it.